Hi, welcome back to my channel. Well, in this video we'll learn a very important experimental design which is widely used in agricultural sciences, especially in case of field of agronomy, and that design is known as split plot design. It's a kind of an experiment within an experiment, so let us proceed. In field experiments, certain factors may require large plots than others. For example, experiments on irrigation, tillage, etc., which are mostly used in agricultural sciences, requires larger areas. On the other hand, the experiments on fertilizers may not require the larger areas. So to accommodate factors which require different sizes of experimental plots in the same experiment, split plot designs have been evolved. So it is a design where two factors are investigated in an experiment with unequal precision. Remember, in a two-factor experiment or a conventional factorial experiment, we used to evaluate factors, two or more than two factors, simultaneously in a single experiment but with equal precision. But in this design, the factors are studied with unequal precision, and in split plot design, the larger plots are called main plots, and the smaller plots within those larger plots, they are called as subplots, and the factors which are allotted to these larger plots, which are main plots, are known as main plot treatment, and the factors which are allotted to subplot are known as subplot treatment. So we can say, in nutshell, this is a design in which a specialized randomization scheme for a factorial experiment is adopted. So we can say it's an extended or specialized version of a factorial experiment. But the only difference between a conventional two-factor experiment and split plot designed with two factors, which involves two factors, one is main plot and another one is subplot, that means both these factors are studied with unequal precision. So some of the important points which are involved in split plot design is it is suitable for factorial experiments where larger plots, which are known as main plots, are required for the application of different levels of one factor. One of the factors is assigned to the main plot, which is a larger plot. The assigned factor is known as main plot factor, and the main plot is further subdivided into subplots to which the second factor called subplot factor is assigned. So this is the factor which is studied with larger precision. Thus each main plot becomes a block for the subplot treatment, that is the levels of the subplot. And the important thing in this design is that the randomization is done in two stages. In a conventional factorial experiment, the randomization of both factors is done in a single stage, but in this case is a two-stage randomization process. That means we randomly allocate main plots first, then within those larger plots we use to evaluate a subplot depending upon the number of levels which are involved in both plots. So the first, the levels of the factor A, say for example main plot, are randomized over the main plots, and then the levels of the factors are randomized over the subplots within each main plot. So in this design, both these factors, main plot and subplot, they are tested or evaluated with unequal precision, with the more precision is given to the subplots and the less precision to the main plots. Now in case of split plot design, there are two distinct error terms involved. One for the main plots, testing the factor A, which is a main plot, and one for the subplot for testing the factor B, which is subplot. The main plot error is larger due to the greater heterogeneity, of course, while the subplot error is small. Comparing interactions using the smaller subplot error increases the precision compared to the simple factorial design. So in nutshell, we can say a split plot design, the factor assigned to the subplot is the factor that requires small amounts of experimental material. So it is of a primary importance and is expected to exhibit a smaller difference, or we can say for which the greater precision is desired. So this subplot is tested with greater precision. Now the important question in case of this split plot design is that the precision of the measurement of the effects are not same for the both factors. So the assignment of the particular factor, either the main plot or the subplot, is extremely important. For example, a plant breeder, say we have a plant breeder and an agronomist, say for example a plant breeder who plans to evaluate, say for example 10 promising rice varieties with 3 levels of fertilization or fertilizers in a 10 into 3 factorial experiment would probably wish to have a greater precision for the varietal comparison than for the fertilizer response, because the breeders are more interested in varietal comparison or varietal evaluation than to the response of the fertilizers. So thus this plant breeder would designate the variety in as subplot factor and the fertilizers as main plot. While on the other hand, using the same 10 promising varieties with 3 different levels of fertilizer doses, the agronomist who wish to study the fertilizer response of 10 promising varieties developed by this plant breeder would probably want greater precision for the fertilizer response than for the varietal effect. So he would assign the varieties to the main plot and fertilizer to the subplot. So fertilizer response is more important for an agronomist in this case, in this example, and varietal comparison or evaluation is more important for a plant breeder. So plant breeder will use these varieties as subplot factor, and he will test them with greater precision. But the agronomist will treat these fertilizers, 3 fertilizer levels, or we can say the 3 fertilizer doses, as subplot, and he will test them or evaluate them in as a subplot factor, because this fertilizer response is of prime importance for an agronomist, and varietal comparison is of prime importance for a plant breeder. Say for example, since it is a fact that there is a 2-stage randomization process involved in case of separate plot design, one for the main plot and another for the subplot. So in each replication, main plot treatments are first randomly assigned to the main plots, followed by the random assignment of the subplot treatments within each plot. For illustration, a 2-factor experiment involves 6 levels of nitrogen treated as main plot treatments and 4 S varieties which are treated as subplot treatments in 3 replication 1, 2, 3. So in step 1, we divide the whole experimental area into 3 blocks. R is equal to 3, R1, R2 and R3, and each of which is further divided into A is equal to 6, because we have 6 levels of nitrogen, 1, 2, 3, 4, 5 and 6. Same with the second replication and with the third replication. And then in step 2, utilizing or following and randomized complete block design randomization procedure with 6 treatments, or we can say A is equal to 6 because there are 6 levels of nitrogen with 3 replications, randomly assign 6 nitrogen treatments. So there's a randomization process involving in adjustment of these 6 levels within replication, and same is the case with second and with the third. And in the third step, we can say in the second stage, divide each of the main plots, that is R multiplied by A, that is 3 multiplied by 6 is 18 main plots, that is 1, 2, 3, 4, 5 and 6. 6 multiplied by 3 is 18. That means into 4 subplots, that is 1, 2, 3 and 4, and follow again a randomization procedure or utilizing a traditional RCBD type of a design for B is equal to 4 treatments and R into A, that is 16 replication, and randomly assign these 4 varieties or 4 subplots in each of these 18 main plots. So there are some important features involved in that. Is the size of the main plot is B times the size of the subplot. So in this illustration, 4 varieties, that is equal to B04, is the size of the main plot is 4 times the subplot, and each main plot treatment is tested R times, whereas say for example N4 1 and 2 and 3 here, but while as subplot is tested A multiplied by R, that is A is the levels of the main plot, that is 6 into R into the number of replicates the blocks. We can say 6 multiply 3 is 18. Thus the number of times the subplot treatment is tested will always be larger than that of the main plot, and it's a primary reason for the more precision of the subplot treatments relative to the main plot treatment. So in this example, each of the 6 levels of these nitrogen were tested 3 times. If we take an example of this N1, here 1, this is 2, and this is 3. But each of the 4 varieties, they are tested 18 times. You can see if we were to take an example of this V11, 2, 3, 4, 5, 6. So again 6 here and 6 here. So 6 multiplied by 3 is 18. So that is why the subplot is tested, or we can say evaluated, with larger precision. So this is a design in which 2 factors are studied in an experiment, but the randomization for the both factors is done separately, or we can say there's a 2-stage randomization, and the factors are studied with unequal precision. Subplot is tested with more precision because of this fact, and main plot is tested with less precision. So the statistical model which is involved in split plot design is this. We have a response variable here, we can say, is the observation of ith replication for jth main plot and kth subplot. Mu is the general mean, r is the replication of the effect of the ith replication, alpha is the level of the factor. We can say this is the main plot, and this is the error which is involved. There are 2 errors involved in this design. This is the effect of subplot, and we can say this alpha and beta, this is the interaction between the main plot and subplot, and this is the overall random error, which is usually normally distributed independently, or we can say identically distributed with 0 mean and constant variance, because it involves a parametric algebraic procedure that is known as analysis of variance. So the traditional ANOVA table, as you can say, we have different columns: source of variation, degrees of freedom, sum of square, mean sum of square, and finally F. So the replication degrees of freedom is r minus 1. For main plot factor, we have a minus 1. So in order to get the main plot error, because we have 2 errors here, one is due to the main plot and subplot error, as a into the levels. A is the levels of the main plot, and in case of factor B are the levels of the subplot, and this is the interaction, and this is the way we used to get the degrees of freedom, or error degrees of freedom, and this is the total degrees of freedom. And like in the traditional designs, while carrying the analysis of variance, we used to get the total sum of square, and this total sum of square is further divided into different categories. Now that depends upon how many sources of variations are involved in a particular design. Since in this design we have 2 factors, one is factor A, factor B, and their interaction, and we have 2 types of errors. And finally F, it decides whether there is a significant difference among the different levels of this main plot factor, or whether there is a significant difference among the different levels which are involved in subplot factor, and whether there is a significant interaction between factor A and factor B. So let us take an example which involves data on grain yield of 4 rice varieties grown with 6 levels of nitrogen in a split plot design with 3 replications. So the nitrogen, 6 levels of nitrogen in this case are the main plot, and 4 different rice varieties, that is V1, V2, V3, and V4, they are tested in or treated as subplot. So we have a data set here. We have 4 different varieties, and 1, 2, 3, 4, 5, and 6 different levels of nitrogen, and they are adjusted in 3 different blocks, rather in replications. So this is the data. So whenever we are doing the numerical illustration while utilizing split plot design, the first thing is that we need to get the two-way tables, which involves the totals only, not the averages. The first one is between the main plot with replication and main plot with the subplot. So we have a two-way table between the levels of the nitrogen and across different replicates. So we need to get the total. Say how we are going to get this N0R1 total. Simply we will sum the values of this R1 across these 4 varieties. This will give us the value of this 15964, that is this plus this plus this and plus this. So similarly we can get this R2 for N0 and R3 N0 and likewise for the rest we can get this. The second step is that we need to get the totals across the columns as well as across the rows, and this in green, so we will get the grand total. Now the second two-way table, which again belongs to the totals only, not the means, that is between the main plot and subplot. That means how we are going to get this N0V1 of 12,758. That is simply will plus these three values of V1 across these three replicate, that is this plus this plus this, we will get this. And similarly for this V2, for this V3, for this V4, we will get the values. Again we will go for the totals or sum across the rows and across the columns, and again we'll get the same overall total, that is grand total. So like in the traditional analysis of variance or the traditional designs, the steps are same. Simple arithmetics, addition, subtraction, multiplication and division. The first step is, as usual, we get the correction factor, that is the square of the grand total divided by the number of observations. Three other replicates. A is the levels of the main plot, B is the levels of the subplot, that is 6, and this is 4 multiplied by 3 is the number of replicate. So 39448 is nothing, is the grand total, and square it, we will get this much of a value which is in yellow color. And total sum of square is summation x square minus correction factor. That means square of each and every individual observation in the original data, that is 4430 plus this square plus this square plus this up to this, the last one, that is 2014 square minus the correction factor. So we will get the total sum of square. Then the replications of sum of square is very simple. The square of replication whole divided by the levels of the main plot and subplot. So we have the replication total, this square plus this square plus this square, and you can see whole divided by the levels of A into B, that is 6 into 4 minus correction factor, we will get the replication sum of square. Then the sum of square A, or we can say the sum of square due to the main plot, that is summation A square, that is nitrogen, divided by the number of replication and the levels of the opposite factor, that is subplot, not the levels of this nitrogen. So like in the factorial experiment we used to do, minus correction factor, that is the square of n0 plus n1 plus n2 plus n3 plus up to n5. N0 is this 4867 square, and this n5 is 69561. You can see whole divided by 3 into 4 minus correction factor. We can get this the sum of squares due to the main plot, or sum of squares due to the nitrogen. Then R sum of square, very simple, the summation of R into A, that means the replication into A. A is the main plot, so we have a two-way total table of the main plot and subplot. That is minus correction factor minus the replication sum of square. The sum of square which are involved in this main plot, that is nitrogen, that is 159640, that is this square plus this square plus this square plus this square plus this square, whole divided by the number of the levels of the factor B or the subplot, minus correction factor which is already collected, minus replication sum of square which is again already collected, the minus sum of square to the main plot which is already collected. We deduct all these values and we will get the main plot error. Then the sum of square due to the subplot, that is similarly to get the total of the varieties, that is v1 v2 square v3 square, that is v1 square plus this is up to v4 square, whole divided by the number of replicates into the levels of the opposite factor, that is nitrogen, that is 6 minus correction factor, we will get this. Then the interaction is very simple, so we have a interaction here also, but we need to deduct this correction factor with the sum of squares due to this variety, that is subplot, and sum of square to the main plot. So again we will use this, then we will get this interaction sum of square. Then error, subplot error, or because there are two errors involved, this is simply total sum of square minus the sum of all sum of squares. So we will use only total sum of square, then deduct it with the values of all these, but we need to add all these values. That is this 20, this is the first one is this replication, this replication sum of square, this square plus this square plus this, and the last one is this So this 699, so then we will get some value and deduct with the total sum of square, so we'll get the error sum of square. Now the last thing is that we have got all the sum of squares. Simply what we will do, we'll adjust these values into an ANOVA table. So we have an ANOVA table here. The replications, the factor A, that is main plot factor, main plot error, subplot, interaction, subplot error, and as per the degrees of freedom we will try to incorporate this. There are 3 replications, that 3 minus 1 is 2. There are 6 levels of nitrogen, 6 minus 1 is 5. There were 4 levels of 4 varieties, 4 minus 1 is 3. And similarly, as per the degrees of freedom which are given in this degrees of freedom column, we will get the degrees of freedom here, and we will put all these sum of squares in this sum of square column, then divide each and every sum of square with its respective degrees of freedom, so that we'll get the mean square. The important thing here is this main plot factor, subplot factor, and this interaction. So we have already calculated this tabulated value, and you know how to calculate it, because whenever we want to test this f, since this f is very simple to calculate, this is very easy to do. That means here we need to get this mean square of mean plot with its mean square error, and for factor b, again we will take this with mean square of the b, and here we will take this value with or we can say it's a ratio, variance ratio test. So for main plot, this divided by its mean square error, and in this case subplot will take this with its mean square error, and this interaction will take this numerator and this as denominator, so that we get it. So in order to get the tabulated value or the critical value of, we need 2 degrees of freedom here, one due to this, and the second one will be here. So 5 and 10 degrees of freedom we will get this one, and 3 and 36 degrees of freedom we will get 2.8, and for 15 and 36 degree error degrees of freedom. So the thumb rule is, whenever the critical value, or we can say whenever the calculated value of a test of significance is greater than its calculated value, and under those conditions, so we used to reject the null hypothesis. That means the 6 different levels of nitrogen, they are significantly different, or we can say at least one pair is significantly different from the rest of the pairs. And same is the case with this and this. So in all these 3 cases we can say there's a significant difference across the levels of nitrogen. There's a significant difference across the 4 varieties with respect to the grain yield, and the varieties, the nitrogen or the response of nitrogen, and on varieties they have got an interaction. There's a kind of independence, and traditionally we can use the same calculation procedure which we have done for the post hoc analysis to calculate the critical differences. That is very simple to get the mean squares for this plot factor A and factor B, and then we will simply use the under root 2 ICMS by R into A and R into B, or we can use only R, but we have to be cautious here. If we are calculating the critical difference of this, so we don't need to divide the degrees of freedom of this, but rather we need to multiply the application with the degrees of freedom of the opposite factor. Same is the case with the second factor. So in conventional analysis of variance, like we used to calculate the critical difference, so we can calculate the critical difference also, but the important thing is your f is significant, so you can give your interpretation based on this. So this is a design which is usually used whenever we are dealing with the factors on an experiment in which factors are studied with unequal precision. So this is the way we can execute design. So thank you very much. Hope you will like this video.